Hey folks, and welcome to this tutorial by Technonan on optical brighteners, or sometimes you might hear them called fluorescent whitening agents. OBAs, FWAs, they're the same thing, okay? So it doesn't matter which they're called, we're talking about the same thing there. Now, I would highly recommend that if you have not watched the brightness series prior to this, that you stop and go back and watch those, because there's a lot of groundwork, a lot of core information that is discussed in those videos that will help you gain a quicker understanding of how optical brighteners work. We will do a bit of a review of some of those topics in this video, but the core of information, you'll really be better off watching that first. So just a recommendation on that. But if you see this guy up behind me, this fella right here, that is not a pleasant picture to me, because that reminds me back to my college days, and I try to forget about those because it's about chemistry. And when we're talking about optical brighteners, that's a molecule of an optical brightener, and optical brighteners are all about chemistry. It is all about how that chemical reaction occurs, and then the physics of light after that, how those two work together to create this pretty unique phenomena that we call fluorescence. Now, fluorescence happens a lot naturally in nature, and there are some interesting things that you can do with an ultraviolet flashlight and go to different places in your world. Some would be good, some you probably don't want to go there twice, but some interesting things you can see with that. More interestingly, though, are things like this. You know, this day glow kind of things, things that fluoresce, okay? These guys all fluoresce in different regions of the spectrum. These out in the green and yellow region, these out in the red region of the spectrum, and that's all interesting. But for us, as paper makers, we want to drive things from a neutral white to a bluish white. Why? Because consumers prefer blue whites over neutral whites or creamy whites, all right? Whether it's in the white clothing that we have and the detergents that we use that have bluing agents and optical brighteners in that, or it's in the paper that we manufacture. If I were to go out and I had two samples, and those two samples were basically optically the same, except one had a blue dye to it, so maybe it was actually a little bit darker, but it was tinted towards blue, a majority of the population would say, I like that blue white better, because it is perceived as a brighter, whiter, cleaner white. And so, as paper manufacturers, we want to be able to do the exact same thing with our product to reward the consumer with what they want to see. So we do that through a couple different ways. One is through adding blue dyes, and we'll talk a bit about that in the last videos of this series, but we'll also talk considerably about that in the color video series that we'll do for you. So those are the two areas we'll see. In this one, we're mainly going to talk about optical brighteners and how they work, okay? So a quick review of some of the things in that brightness video that's important that we review here again. All right, so if we define the visible spectrum as 400 nanometers to 700 nanometers, okay? That's what we see as light. Anything below 400 nanometers we call UV or ultraviolet energy. Anything above 700 nanometers we call the IR or infrared region of the spectrum. So we've got those three spaces. Now within the visible region, things we respond to as light, we break that down into three spaces as well. We say 4 to 500, this energy here, we call that blue light energy. And then from 500 to 600, we call that green light energy. And then from 600 to 700, we call that red light energy. So real simple, blue, green, and red light energy with that. Now if you think back to that bleaching process that we talked about and what happens during that sequence, well, we're going from something like an unbleached box or a grocery bag, and it would have an energy distribution look something like this. And as we step through that bleaching process, we see that the greatest area of change is happening over here in this blue region, right? So as I go through that bleaching process, I'm removing yellow from that, okay? Making the paper bluer to some extent, because yellow is the opposite of blue. So if it's getting less yellow, it's got to be getting more blue in a sense. But no matter how hard I try in the bleaching process, it's always going to tail off over here in this blue region of the spectrum. So naturally, paper is going to have a little bit of that creamy tint to it. So what do I do to shape that? towards blue as I add those blue dyes or add an optical brightener. Now, an optical brightener or a fluorescing agent is going to absorb light in one region of the spectrum and re-emit that light in another region of the spectrum. Well, it just so happens that an optical brightener, its goal is to re-emit energy here in the blue, giving us additional energy in the blue. Well, where does it absorb energy? It absorbs energy in the ultraviolet region. Now, the ultraviolet region, my eyes don't respond to that, so I don't lose any visual energy by absorbing ultraviolet energy, and I bring that, so if this energy was coming off like this, now with an optical brightener, I'm absorbing this energy here, and I'm bringing it back over here into the blue region of the spectrum where brightness is measured, and I'm getting more energy there. I'm getting this fluorescing effect, and now I see that as a brighter, whiter, cleaner sheet because of that fluorescing that's occurring with that. So that's what an optical brightener is designed to do. Now, how that actually works is, again, a real quick little chemistry thing here, right? So you've got your molecule. You've got your molecule of your optical brightener in there, and you've got electrons that are orbiting around that, moving around that. Now I add the optical brightener in there. Okay, I got the optical brightener in there, and now I strike that with ultraviolet energy because this optical brightener responds to UV energy. That excites that electron, and that electron now goes to the next orbital level. It's out here at this next range, and it's going to circle there for a while, and then eventually it wants to come back to its natural state. It wants to return home. Okay, when it goes from this outer orbital to its home, it gives off energy, and that energy is what we see here in this blue region of the spectrum, and it's a continual process in there of all those molecules all interacting with that UV energy to cause that fluorescing effect, giving us that additional energy that we have with that. Okay, so again, whether it's these guys over here and that fluorescing is occurring in different regions of the spectrum, or it's with the optical brightener, it is that absorbing of UV energy and then that re-emitting of that energy in the blue region of the spectrum, driving that sheet brighter, whiter, cleaner. Okay, so what we're going to do now is we're going to take some samples and we're going to change the lighting in the room so you can see it better. But we've got three ultraviolet light sources. Okay, so they have some violet energy, but they also have a lot of ultraviolet energy with that. Okay, then we've got three samples here. These two samples contain water and unoptically brightened pulp, just some tissue that I've dissolved up in that water. This is just a flask of water. Okay, we will introduce optical brightener to this flask, and you can see what happens. We'll introduce optical brightener to this beaker of pulp slurry, and you can see what happens, and we'll compare it to the one that we won't touch at all. Okay, so you'll have some visuals of exactly what we're talking about here. All right, so as it turns out, actually, with these very rich UV light sources, my shirt was overwhelming the camera, so I had to put black jacket on just to kind of take the light energy down, just so this could work. So what we have here, again, we have two ultraviolet light sources here and a third lamp there. Okay, so those guys are very UV rich, and they're illuminating this environment down here. Okay, so again, if I put up our day glow very brilliant samples, you can see that they project a lot of energy in different regions of the spectrum. If I bring back this sample, you can see again there's a lot of fluorescence in that. If I put this one in front of it, you can see there's very little fluorescence with that. So again, that's what we're talking about when we talk about optical brighteners. Now, to get into exactly what we were going to do, so what I've got here again is just a flask of water, and I'm going to take some of this optical brightener here, and I'm going to pour it into that water, okay, so that you can see the reaction that occurs from that. Now, the optical brightener is kind of a yellowish color, okay, so that's what this is naturally in this bottle. But as I pour this in there, and I'll try to pour as little as possible, just a little drop, you can immediately begin to see the reaction that occurs there. And so I'll move that around a little bit. Now you can see this, it was fairly flat and maybe a little bit violet color. Now it's got this very bright light blue tint to it, okay? And again, it is that optical brightener now absorbing this ultraviolet energy and re-emitting it over here in the blue region of the spectrum, just like we had talked about, okay? Now we're going to move this over here, and we'll move these two samples forward, all right? So now with this, what we have, again, are are two identical samples here, and they have non-optically brightened tissue in it. So if I just take this screwdriver and I'll swirl that around and I'll pull a little bit of the pulp up there, and you can see it's giving that kind of that violet color to that. And I can swirl this around, grab a little bit of that pulp, and it's the same thing there, violet color with that, which is just that white reflecting the violet nature of this light source here. Get my optical brightener again, and instead of pouring it this time, I'm just going to, just to make sure I keep my amount to a small amount, I'm just taking this pencil, I'm moving around the optical brightener, and I'm going to bring it over, and I'm going to introduce that optical brightener to this. Now you can see a drop hit that optical brightener, a drop of that optical brightener hit that pulp and that water, and you can see immediately the reaction starting to occur. And I'll stir that up a little bit now, and you can see that now dispersing throughout that, and you have this very intense glowing sample here. The only difference now between this sample and this sample is the introduction of the optical brightener. So we've taken a sample that was flat, basically, and no excitation, to one that's glowing quite a bit. So now if I take and I pull some of that fiber out and I just set it there, okay, you can see that very brilliant with that. And I bring this guy out, and it's the same as it was, and it's that violet, almost kind of grayish, not a lot of light reflecting from that. And so that's the impact of the optical brightener, really driving that sample to look like that. Okay? So that's those two guys. All right, let's move those back over here, and we're going to bring this guy back. Now, let me just step off here for a second and grab a tissue again. And so I've got another one of those non-optically brightened tissues here. And now I'm going to take that, and so this is my very dilute solution of optical brightener in water. And I'm going to take this fiber, I'm going to take this tissue, and I'm going to set it down in there. And you can watch as this changes, okay? So you can see when it comes in contact with that surface, and you can see that water wick up into that, and that water contains the optical brightener, and that optical brightener is just wicking up into that sample, and now that sample is almost like it's almost like a light source. It's glowing in energy. So you can see that very clearly with that. I take that and I just put that back down in there, and it will just continue to wick up in there, and you've got that sample. So this sample is identical from here to here, with the exception of the presence of the optical brightener. So that's making all the difference in the world. Okay, now I'm going to take that and I'm going to turn off one light source. Okay, I've turned off one light source. I'm going to turn off another light source. Okay, then I'm going to turn off this light source. And when I do that, what happens? Well, you lose the effect of the optical brightener, because now you don't see much difference from side to side, from non-optically brightened to optically brightened. And that's because the optical brightener is all dependent upon ultraviolet energy. If there is no UV energy in your environment, there's no UV energy to be absorbed. Thus, there's no UV energy to be re-emitted. Okay, so if you're in an office environment, and an office environment has a lot of cool white fluorescent tube lighting in that, those light sources have minimal UV energy. Or now with the LED technology that's coming into place, most LED light sources you see have very little to no UV energy, so you don't get that fluorescing effect. Alternatively, if you go out outdoors and you view this outside, that sample with a lot of optical brightener would just be jumping off the page at you, be very brilliant with that. So optical brighteners are all dependent upon the amount of UV energy that you have here. Okay, so you're going to absorb from 400 down to maybe even as far as 350, 340 in that region with some of the experimentation we've done here. That light will re-emit in the 420 out to 440, maybe out to 450, but you're going to find most of it emitting out here in the 420 to 440 region of the spectrum. Okay, so it's driving that sample bluer in that region of the spectrum. Okay, so that's a real quick overview of how an optical brightener works. In the next video, we're going to talk about, in particular, tappy brightness and how we measure the effect of the optical brightener, how it's measured on a tappy instrument. Then we're going to go to the ISO procedure and talk about how the ISO method has us evaluating the effect of an optical brightener. And then in the next video, after that, we'll talk about color and the effect that optical brighteners have on colors. And that's where it gets a little bit more complicated, because we're talking about driving the sample blue. And we drive the sample blue by two ways, right? One through optical brighteners and one through dyes. And if they're both going after the blue region, then we have to be able to, how do we separate those two? How do we distinguish those two? So we'll talk about some of that there as well. As always, guys, we're hitting the surface on all these topics, and if you have questions, please do not hesitate to contact us. If there are things in relationship to optical brighteners you would like to have a phone call with, or have us come to your facility to work with you, we're always more than glad to do that. So give us a shout and let us see how we can help you improve your process, and at the end of the day, hopefully we can help you make better paper. Thanks for watching.